Welcome back, physics enthusiasts. I'm Swati, and let's do some multiple choice question on topic electric potential and capacitance. Let's begin with that. Okay, students. So the first question is: some charge is being given to a conductor, then its potential is maximum at surface, is maximum at center, remain the same throughout the conductor, is maximum somewhere between surface and center. See, the potential is remains same throughout the conductor. If it is a conductor, spherical shaped conductor, so you know that electric field is zero inside the conductor and V is constant. Okay, from center to its surface, it remain constant. It is something like this. If we uh, make a graph between V and R, then it remains constant till its surface, and then it decreases with 1 by R. Okay, so it remains the same throughout the conductor. Next, a positively charged particle is released from rest in a uniform electric field. The electric potential energy of the charge remain a constant because the electric field is uniform, increases because the charge moves along the electric field, decreases because the charge moves along the electric field, and decreases because the charge moves opposite to the electric field. Okay. Actually, the potential decreases in the direction of electric field, and positive charge basically moves in the direction of electric field. So here the potential decreases, and the positive charge moves in the direction of electric field, so its potential energy decreases because the charge moves along the electric field. So C is the correct one. Next, question number 3 is figure shows some equipotential line distributed in space. A charged object is moved from point A to B. Okay, so work done batana hai. So for the work done, it's charge into change in potential. Now, if you see from A to B, it's always from 40 to 20, right? The distance between the plate doesn't matter. The charge is same, the potential difference is same, it's 40 minus 20. So the work done is same in all the three figures. That is option number C. It is same in figure 1, 2, and 3. Okay. Next, question number 4. An electrostatic potential on the surface of a charged conducting sphere is 100 volt. Okay. On the surface, right, of a charged conducting sphere. So it means it is same throughout the sphere. It is 100 volt. So S1 is at any point inside the sphere, electric intensity is 0. Yes, because potential is constant, and you know E is equals to dV by dr. So if V is constant, then its derivative is 0. At any point inside the sphere, the electric potential is 100 volt. Yes. So it is 100 volt at everywhere. That means it's constant. So its electric intensity is 0. So S1 is true, S2 is also true, and S1 is the cause of S2. Okay. Equipotential at a great distance from a collection of charge whose total sum is not 0 are approximately spheres, planes, paraboloids, and ellipsoids. So basically, at a great distance, when the distance increases, the charge behave as a point charge. Okay. So at a great distance and whose sum is not 0, so there are approximately spheres in shape. Okay. Planes for like uniform field, and parallelopipes and ellipsoid, no, so it's behave as spheres. 4 capacitor each of 50 microfarad are connected as shown. Okay, so this is 50, 50, 50, and 50. The DC voltmeter V reads this shows 100 volt. So that means this is connected to both these two capacitors. So if you calculate the total capacitors, so this is in parallel. So here the C equivalent is basically 50 plus 50, that is 100 microfarad, or you can say 10 raised to the power minus 4 farad. Now if V is the charge, then Q, total Q here is what? CV, that is 10 raised to the power minus 4, and V is what? 100. So this become 10 raised to the power minus 2. So total charge on these is this. The charge on one is, since the capacitor is equal, so charge can be divided equally on both the capacitor, or you can get Q1 by C2 over C1 plus C2 into total charge. You can use this formula, and you can also get, since see, you can say that on both the capacitor the total charge is 10 raised to the power minus 2, and also here is 10 raised to the power minus 2, because they both are in series. Now individual will have half of this, that is half of 10 raised to the power minus 2, that is 0.5 into 10 raised to the power minus 2, or 5 into 10 raised to the power minus 3, because the capacitor are same. If they are not, so what we can do, we can simply use the formula to calculate the charge on one is C2, the other one, over C1 plus C2. Or sorry, C1 over C1 plus C2, because it has a direct relation. It's not inversely proportional. If it is inversely proportional, then C2. If you want to calculate charge on one, then you can put C1 above. It's like this. Okay. And since here the charge is, the capacitor is same, you can simply divide it. The variation potential V with R, electric field E with R for a point charge is correctly shown. See, potential is also inversely proportional to R, and electric field is R square. So both have these type of curves, but at some point they cross each other, and it is like this. That is B. Okay. Okay. So the next question is, a parallel plate capacitor is made of two dielectric blocks in series. Okay, one of the block has thickness D1, dielectric constant kappa 1, other has D2, kappa 2 or K2. The arrangement can be thought as a dielectric slab जिसकी total thickness is D1 plus D2, and we have to calculate K. Okay, so for C1 it is basically A epsilon naught kappa 1 by D1, and C2 is A epsilon naught kappa 2 by D2. Okay, simply calculate C equivalent, which is 1 by C equivalent, 1 by C1 plus 1 by C2, and this become D1 over A epsilon naught kappa 1 plus D2 A epsilon naught kappa 2. You can take 1 by A epsilon naught to be out, and this becomes D1 by kappa 1 plus D2 by kappa 2. Okay, and if you want to take LCM, then this become kappa 1 kappa 2. I think I should do somewhere else. So your 1 by C equivalent is equals to 1 upon A epsilon naught kappa 1 kappa 2 D1 kappa 2 plus D2 kappa 1, and C equivalent will become A epsilon naught kappa 1 kappa 2 D1 kappa 2 plus D2 kappa 1. Okay, now in actual C equivalent is A epsilon naught upon total D, which is D1 plus D2 into K equivalent. And if you compare both, so K equivalent upon D1 plus D2 is equals to kappa 1 kappa 2. I think you can C equivalent actually is A epsilon naught upon total thickness into K kappa equivalent. Now if you compare both, then this term is equals to K epsilon naught upon D1 plus D2. That is D1 kappa 2 plus D2 kappa 1. Now this D1 plus D2 goes up, and it somehow become this, but here the denominator value is not right. It should be kappa 1 D2 kappa 2 D1. It is like this. It's simple. If say parallel, then you have to simply C equivalent plus C equivalent. Oh, sorry, C1 plus C2. And then you can compare it with. Okay. Now, equipotential surfaces are closer in regions of larger electric field compared to region of lower electric field. Yes, will be more crowded near sharp edges of conductor. Yes, because the sharp edges of conductor have high charge density, so high electric field. Will be more crowded near regions at large charge densities. Yes, will always be equally spaced. No, it is not always equally spaced. Equal spaced means, uh, I think, uniform potential, but it's not always equally spaced. So A, B, C are the correct one. Okay, it's more closer. We have a large electric field. So if it is equally spaced, then it shows uniform field. Okay. Next, our 2 microfarad capacitor is charged to 200 volt and then a battery is disconnected. When it is connected in parallel to another uncharged capacitor, the potential difference between the plates of both is 40 volts. See, if it is disconnected, then यहाँ पे charge is constant. So charge is basically C1 V1 before charge is equals to after connection, and they are connected in parallel. So C1 plus C2 into V. The charge before and after is equal because you have disconnected the capacitor. So now C1 is 2 microfarad into V is 200. Another is basically uncharged. It has no potential, so it's 0, no charge. And then C1 is 2 into 10 raised to the power minus 6. And you have to calculate the capacitance of another. So put X here and total potential of 200. So this becomes 4 into 10 raised to the power minus 4 is equals to, okay, just multiply this. This becomes 4 into 10 raised to the power, sorry, here the total potential becomes of 40 volts. So this should not be 200, this should be 40. Now you can multiply it. So this becomes 4 to the 8. Into 10 raised to the power minus 5 plus 40x. And for minus 4, we can do 4 into 10 raised to the power minus 4 minus 0.8 into 10 raised to the power minus 4 is equals to 40x. And 4 minus 0.8 is 3.2 into 10 raised to the power minus 4 divided by 40 is equals to x, the capacitor. 4 ones are 4 eights are 32, and this goes 2 zeros goes up, then become minus 6, that is 8 microfarad. C is the correct answer. It's a calculation. The basic thing is, if the capacitor is disconnected, then put charge to be equal. Next, n identical capacitors are joined in parallel with charge to a common potential V. The battery is connected. Now the capacitors are separated and joined in series. Okay, so I'm erasing this thing. You can pause, you can check the solution. Now n identical capacitors are joined in parallel. You have capacitor n identical and everybody has a potential of V. Now battery is disconnected. If it is disconnected, charge same. And they are now joined in series. This, each will have C. Each have capacitor C because it is n identical. Each have capacitor voltage of V. So each has charge always Q. Same. Okay. So when it is connected in series, again the charge is same. C is also same. So V will remain also same. So total V equivalent is V plus V plus V, that it becomes N times of V. The potential difference will become Ne. Okay. Now, if you talked about energy, because they have also asked energy. So here the energy is half CV square area, half U square by C. And here also it is same because nothing is changing. If you check the individual energies. So if you count here, it also n times of U, and here also it's n times of U. So energy will remain same, but the potential difference will become NV. Interesting question. Next, a capacitor of a capacitance becomes 7 by 6 times its original value if a dielectric slab of thickness T is equals to 2 by 3D is introduced in between the plates, where D is the separation between the plates, so dielectric constant. C dash is basically 7 by 6 times of C equivalent original value, dielectric slab of this thickness, so it is A epsilon naught upon D minus T plus T by kappa is the formula. And where D is the separation between the plates, A epsilon naught will remain same upon D is 7 by 6 times. Okay, so you can cancel this two terms. It becomes 6D is equals to 7 times of D minus, put the value of T which is 2 by 3D plus 2D by 3 kappa. And then it becomes 6D, 7. 3 minus 2 is 1. D by 3 plus 2D by 3 kappa. You can cancel D, then it becomes 6 is equals to 7. Take the LCM, 3 and 3 kappa is 3 kappa. 3 is there, multiply kappa plus 2. You can cross multiply it. 6 3 is the 18 kappa. And 7 kappa plus 7 2 is the 14. 18 minus 7 gives you 11. And here the value of kappa or dielectric is 14 by 11. That is A. Okay. Just remember the formula. It's important. Next. The plates of a parallel plate capacitor are 4 centimeter apart. The first plate is at 300 volt and the second plate is at minus 100 volt. Okay, so let's take, there are two plates and basically one is at 300, other is at minus 100 and it is separated by 4 centimeter apart. And we have to calculate the potential at 3 centimeter from the second plate, that is from minus 100 plate. Okay, somewhere here. What we will do, we will find the electric field. Since the electric field is uniform between the plates, it is same. You know, for a parallel plate, the electric field remains same at whatever distance. So we will find electric field at its midpoint. So E is equals to what? Minus of delta V by delta R. So minus, let's take minus 100, minus 300 and the distance between them is 4 centimeter. So that become minus 400, that is plus 400 by 4 into 10 raised to the power minus 2. Minus 2 goes up, 10 raised to the power plus 4 volt per meter is the electric field. Now, the electric field we have calculated for a distance of 4 centimeter and it is also the same for 3 centimeter because it is uniform between the plates. So this E is also equals to, let's take this potential as VO. So it's VO minus sign above minus 100 upon the distance between them, that is 3 centimeter. And that electric field is basically 10 to the power 4 into 3 into 10 raised to the power minus 2 is equals to minus V naught minus plus minus 100. Okay, so that becomes 300 minus V naught minus 100 and I think let's do the calculation again. The electric field is basically minus delta V, that is minus 100 minus V naught upon the distance, which is 3 into 10 raised to the power minus 2. So electric field is 10 raised to the power 4 into 3 into 10 raised to the power minus 2 is equals to 100 plus V naught. Okay, so this becomes 300 is equals to 100 plus V naught. Then it is 300 minus 100 V naught, that is equals to 200 volt. That is option number A. Okay, so it has asked from second plate, so we did 100 minus this from final minus initial because it asked from 100. volt plate. Interesting question. Next, in the case of a charged metallic sphere, potential V changes with respect to distance r from the center. Initially, it remained constant, and then it follows 1 by r square. Here it is 0, so it's not linear. It's not linear here. This is also wrong. So basically, B option is the correct one. A conducting sphere of radius r is given a charge q, the electric potential and electric field at the center of the sphere. At the center, the potential will remain same, that is kq by r, whatever be the radius. And the electric field here is 0. So B is the correct one. Now, 4-point charges are placed one at each corner of the square. Minus q, minus small q, 2q, and the relation between q and small q, for which the potential in the center is 0. If V here is 0, let's take this distance to be A, which is same for all because it is a square, symmetrical. So just get the potential to kq by r. So kq is 2q, r is A, plus k2 small q by A minus kq by, because in potential you have to consider the sign as well, minus k small q by A equals to 0. Then if you solve these two terms, it becomes kq by A. If you solve these two terms, it becomes k small q by A equals to 0. Then it is minus kq by small a, and q is equals to minus q. That is option number B is the correct one. Okay, very simple. Next is an electric dipole consists of charges plus q minus q separated by a distance L is in stable equilibrium in a uniform electric field E. So the electrostatic potential energy is basically minus Pe cos theta. Now if it is in stable equilibrium, then theta is 0 degree. So U is equals to minus Pe, and basically P is one of the charge into the length, that is minus QLE. So C is the correct one. Okay, so the next is, if a positive charge is displaced against the electric field in which it was situated, then work will be done by the electric field on the charge. No, because it moves against. The electric intensity of electric field decreases. There is no change in electric field due to displacing the charge. Energy of a system will decrease. No, it will increase because the potential energy increases because the work is done against the electric field. So energy will be provided by external source displacing the charge. Yes, since it is moving against, so an external energy is required. So D is the correct one. A capacitor of capacitance C1 and C2 are connected in parallel. If a charge Q is given to the combination, the ratio of the charges on the capacitor C1 to the charge on C2. Okay. So if they are connected in parallel, so they have same potential. So Q1 should be equals to C1V, Q2 is equals to C2V. Right? So on each has a ratio of C1 by C2. Simple. Next, a charge Q is kept at the center of a circle of radius R. A test charge Q0 is carried from a point X to Y on this circle such that XY subtends an angle of 60 degree at the center. Let's mark this point as XY. This is 60 degree and a charge Q is here. The amount of work done. Since the potential is same inside the sphere and on the surface, so V at X is equals to V at Y. So if you talk about work done, that is Q, Vx minus Vy, then it would be 0. Okay. A charge Q is uniformly distributed over the surface of a spherical shell of radius r. The work done bringing a test charge Q0 from its center. Again, from center to surface, here the potential is same. So no work is done. 0. A free electron and a free proton are placed between two positively charged parallel plates. Both are closer to the positive plates than the negative plates. The force on the proton is greater than the force on the electron. See, F is equals to basically QE. And electric field is same between the plates. So both will have the same force. Electric field is basically from positive to negative. So this will get force here and this will get force here, but the magnitude wise it remains same. Only the direction is different. Okay, so let's consider one. Then the potential energy of the proton is greater than that of electron. Also, the potential energy magnitude wise is same because it's QV. So if you take V, the potential energy, if you take the work done, that is QV, and both are at the same level. So magnitude wise, the potential energy of both is same, right? Because charge is same. And if you talked about V, so both are at the same level. So V is also same because electric field is same. So if you take V as E dot dr, so that also comes out to be same because they are at the same dr position from both these plates. So I think first and third, but the force is greater is not possible. So first cannot be. So potential energy is same, but if you check the magnitude wise, so the potential energy of proton is positive if you take the sign, and for electron it's negative. So magnitude wise is same, but if you consider the sign, then the potential energy of proton is more greater than the electron. So can take second option. Next, two charges 14 microcoulomb and minus 4 microcoulomb are placed at this and this in an external electric field. The electrostatic potential energy. So here the potential energy has the formula of K Q1 Q2 by R plus QV. So Q1 into V at its position and Q2 and V, the potential. So if we talked about V, it is equals to E dot dr minus. So this become B dot R square into dr, and if you integrate it, minus B by R. So V is equals to B by R. Fine. So now let's calculate individual components. First, K Q1 Q2 by R, that is 9 into 10 raised to the power 9. Q1 Q2 is 14 micro, 4 micro with a minus sign because 1 is negative, upon me distance, and the distance between them is 24 centimeter because they are placed from origin to 12, minus 12 and 12, that is in the total 24 centimeters. So minus 2 will go up, and 4 ones are 6 are 3 3s are 9, 3 2s are 2 7s are 7 3s are 21 minus, and minus 6, this is plus 2. Okay, so minus 6 is minus 12, minus 12 plus 2 is minus 10, and minus 1, so it's minus 2.1 joule. Now next is the potential on charge 14 microcoulomb due to this electric field. Now that would be 14 into 10 raised to the power minus 6, and potential is B by R. B is 1.2 into 10 raised to the power 6, and R, basically it is placed at a distance of 12 centimeters. So let's take 12 and 100 there, cancel, 0.0, 12 and 12. This becomes 140 joule plus 140 joule. I have taken V here. It's plus 140, and then the other last one is minus 4, so it's minus 4 into the potential, that is B by R, and here the R is 12 because from the origin it is 12, and B has a value of 1.2. So this become basically minus 4 into 10 raised to the power minus 6 upon B is 1.2 into 10 raised to the power 6 and 12 centimeter into 100. Right? Minus 6 cancel. 0, 10, become minus 40. So 100 minus 40 is 100. So minus 2.1 plus 100. So if you subtract 100 with 2.110 minus 1 is 9. 9 minus 2 is 7. It's 97.9 joules. Okay. So the electric potential energy topic is very important. And in this particular, it is when the electric field is also present. You have two types of things. One, in the absence of external electric field and in the presence of external electric field. Everything is important. Okay. Okay. So I am erasing this a little bit. Next, a variable capacitor is connected to a 200 volt battery. If the capacitor is charged from 2 microfarad to x microfarad, the decrease in energy is this. Okay, simply put half CV square, subtract that and make it equals to this. Okay, if the capacitor is charged from 2 to x, the decrease. So the energy is decreased. So basically half. Let's take C to be 2 into 10 raised to the power minus 6 because that value is high. Because when it changed from 2 to x, the energy is decreasing. So I'm already taking 2 into 200 volt, that is 4 into 10 raised to the power 4, 200 square, half CV square, minus half, other C is x, into, let's take it C only, into the battery is 200, that is 4 into 10 raised to the power 4 is equals to 2 into 10 raised to the power minus 2. This is 4 into 10 raised to the power minus 2 minus, let's take it microfarad into 10 raised to the power minus 6 as well, so that your values of 10 raised to the power will remain same. So C into 10 raised to the power minus 2 is equals to 2 into 10 raised to the power minus 2. So take this term first, cut these three things, then C is equals to 4 minus 2, that is 2. So 2 is the correct answer. That is option number B. Okay, you can pause and you can check the solution. Next is 4 charges minus Q plus Q and plus Q are placed at the corner of a square of side 2L, the electric potential at a point A. It's very easy, just join it. Because in potential you don't need any vector thing, so you can simply add that. This is 2L because it is a square, so this is L because A is midpoint, and if you take the Pythagoras, this becomes root 5 times of L. Similarly, root 5 times of L. Then total potential at point A, first because of this plus Q is KQ by L. Then because of this plus Q is again KQ by L. Then because of this minus Q is minus KQ by root 5L. And because of this is minus KQ by root 5L. At this, it becomes 2KQ by L minus 2KQ by root 5L. Take 2KQ by L out, this becomes 1 minus 1 by root 5. I think this is the correct one. K 2Q by L 1 minus 1 by root 5. Okay. Next, 3 charges 2Q minus U lies at the vertices of a triangle. 2Q minus Q minus Q, the value of E and V at the centroid. If we talked about the centroid, then the distance from this charge, and this charge is same. So let's take 2BA. So if you talk about potential, then it is K 2Q by A minus KQ by A minus KQ by A, that is equals to 0. So V equals to 0 is the correct one. You don't have to calculate the value, just the think it whether it is 0 or not. So for E to be 0 or not, you can simply say that for the 2q, the electric field would be in this direction, and for the minus q, they're in this direction, where whose resultant is also in this direction. So electric field are not in the opposite direction, so it cannot be equals to 0. So V is 0, E is not equals to 0, so C is the correct option. Next, two parallel plate capacitor X and Y have the same area of plates and same separation between them. X has air and Y has dielectric of dielectric constant C. So C1 is basically C and C2 has a dielectric constant of 2, so it becomes 2C. They're connected in series to a battery of 12 volt. The ratio of the electrostatic energy X and Y. So basically, if they are in series, so C equivalent is C into 2C over C plus 2C. That is 2C square over 3C. 2 by 3 times of C is C equivalent. So total charge Q would be what? So you can simply calculate by half CV square. Okay, so the total charge will be, see, it's very easy. You don't need to calculate total charge. What they have is basically the ratio of the electrostatic energy. So for the energy, you can use the formula of half Q square by C, right? Because they are connected in series, so Q will be same. So all you have to do is you have to calculate the ratio of X and Y. So basically just take the ratio of their capacitor. Ux by Uy is equals to Cy by Cx. Okay. So Cx has air, so it has a capacitor of C, and Cy has a dielectric of dielectric constant 2, that is 2C. So the ratio would be 2:1. As simple. And if it is parallel, then use half CV square because V is constant there. Next, a capacitor plate are charged to a battery of V volt. After charging, the battery is disconnected. That means Q is constant. Across a dielectric slab with dielectric constant K is inserted between the plate, the potential across the capacitor. See, if dielectric constant kappa is added, then you can remember that table. So else you can learn that C will become kappa times Q will remain Q dash. So V dash is equals to what? Q dash by C dash. Q dash is Q, C dash is kappa C, that is 1 by kappa times of original V. So it's V by kappa. Okay. Three capacitors 2, 3, 6 are joined in series. The equivalent capacitance, very easy. In series, you have to reciprocal it. 1 by 2 plus 1 by 3 plus 1 by 6. Take LCM 6. 3 plus 2 plus 1, again 6, 1. So it's basically 1 microfarad. Which of the following is not the property of equipotential surface? They do not cross each other. The rate of which is not the property. The rate of change of potential with distance on them is 0. Yes, it's 0. For a uniform electric field, they're concentric spheres. No. They do not cross each other. Yes, they do not cross. For uniform electric fields, they are like parallel plane sheets. They can be imaginary spheres. So C is the appropriate one. They can be imaginary spheres. The point P lies at a distance x from the midpoint of an electric dipole on its axis. Electric potential is proportional to. Electric potential is proportional to x to the power 2 and electric field is x to the power 3. 1 by x3 and potential 1 by x square. Okay, so this is the last question and we are done with our MCQs on electric potential and capacitance. Again, important chapter, and we are left with our last chapter, that is electric field, electric charge and fields, and I will post it today or maybe tomorrow. And we are done with our multiple choice questions, which are very good practicing questions. And okay, so thank you for watching this video, and do like, share and subscribe. It's just your exam time. So okay, we'll meet you in the next video.